Hello and a warm welcome. Our webinar today goes out to our customers, students, interested engineers, and last but not least, to our competition. My name is Emilio Meza, and I'm your moderator for today's webinar, titled Gate Driver Principles, Considerations, and the Selection Process. This webinar goes from the basic knowledge on why we need a gate driver, its basic functionalities, determining which gate driver is needed, and other considerations in operating a gate driver. During the webinar, Adyatmika will explain several considerations for selection and application of gate drivers, from general principles of switching and IGBT to the main considerations in selecting a gate driver and its gate resistors. Before we get started with the presentation, some words about our webinar platform. In case of connection issues to the presentation stream or to the sound, please try to reconnect using the button on the very top of your browser window. In your browser, on the right-hand side, you see the chat window, which you can actually hide to increase the presentation window. In case you have any comments or difficulties, please let us know via the chat. All messages are private and only we can see them. If you have any questions about the content, please mark your comment as a question with the Q&A mode button. We will try to answer your question at the end of the presentation, and the questions we do not manage to answer today will then be answered by email during the next days. Also, you can send us an email to webinar@semikron.com at any time, and we will get back to you as soon as we can. Finally, we will also share the slides as a PDF file at the very end of the presentation. You will see a download button just below the chat window. Your presenter today is Adyatmika Dharmanandana. Adya received his Bachelor of Engineering at Karlsruhe University of Applied Science before becoming a test engineer for integrated servo drives development. He then completed a Master's of Science at Munich University of Applied Sciences, after which he joined the product manager group at Semikron last year. Enjoy the webinar. Adya, the floor is yours.
Thank you, Emilio. So this presentation will be divided into 6 parts. Before we discuss the driver itself, I want to introduce to you the Semikron profile. After that, I will explain to you generally what is a gate driver and why we need them. Then we move into a more detailed topic about the mechanism inside an IGBT that is relevant for a gate driver. Based on that, we will discuss the basic consideration of a gate driver, where I will explain aspects like current capability, the gate resistors, isolation coordinations, and other bits of advice for the application. The next part of this presentation will be about the protection features. I will try to explain to you the general mechanism of features like short circuit protection, the soft turn off, and also about the other features like dead time, short pulse suppression, etc. In every topic, I will also give you a clue of what features a Semikron driver has. In this regard, I will show you an overview of Semikron driver product portfolio, and lastly, I will summarize the key points of this presentation. Semikron is one of the world's leading manufacturers of power modules and systems, primarily in the medium output range. Today, Semikron has a staff of approximately 3,000 people in 24 subsidiaries worldwide. This international network, with production sites in Germany, Brazil, China, France, India, Italy, Slovakia, and the US, ensures fast and comprehensive service for our customers. Our products help in the realization of energy-efficient motor drives and industrial automation systems. Further applications include power supplies, renewable energies, and electric vehicles. Semikron's innovative power electronics products enable our customers to develop smaller, more energy-efficient power electronic systems. These systems, in turn, reduce the global energy demand. We offer a complete range of industry-standard modules. For example, the mini-skip, that is the first market standard for low-power IGBT module. The semi-trans, that is a screw-type market standard. We also offer stacks. These platforms integrate advanced technologies which maximize performance and power density. For our automotive application, we have highly integrated inverter systems for electric mobility. In the top corner of this slide, we have the IGBT driver. That is our main topic in this presentation. In power electronics, the term gate driver generally used to describe circuitry between a low voltage controller and a high voltage power module. The basic function of a gate driver is to convert and translate the signal coming from the controller to the level that is needed to turn on or turn off the power module, as shown here in the picture. With its name, the signal should be connected to the gate, so the power module will be turned on, which means a current can flow from the collector to the emitter, here marked with the IC, the collector current. Usually, a gate driver also provides isolation to safely separate the high voltage and low voltage parts. A full functioning gate driver should also have the necessary power supplies to define the voltage level that are required by the gate, and it can also have some other features for the system protection. Depending on the application, a gate driver can be integrated with other functions on a single PCB, but in this presentation, we intended to assist you in the selection and implementation of an off-the-shelf driver. If you look at the market, you will find a gate driver available in the form of an IC or integrated circuit, the driver core, or plug-and-play driver. A driver IC may come as a basic lever shifter, or it comes as a full function of logic and isolation. But due to limitation through its package, it may be limited to lower power application only. A driver core can, in contrast, be used for medium to high power application. It comes with all functionality of a gate driver. To be noted, an adapter board is needed to place the passive components and to connect to a power module. The last one is the gate driver that is designed to be directly compatible with certain industry standard module packaging. For example, the Semikron 10 and the Semikron 3 press fit. Before we discuss the mechanism and consideration of a gate driver, we need to understand the IGBT itself to know what a gate driver actually drives. The fabrication of any insulated gate transistors yields three main intrinsic capacitances. These are the CGC, or we can call it the Miller capacitance, the CGE between the gate and emitter, and the CCE between the collector and the emitter. To determine the needed output power capability of a gate driver, it is input capacitance, the sum of the CGC and the CGE, that we need to consider, as they most strongly determine the gate voltage and current characteristics of the gate. Basically, what a gate driver does is charge and discharge these capacitances, this CGC and CGE. For the sake of simplicity, I will further call these capacitances as gate capacitance. There are at least three methods to charge and discharge the gate capacitance. First, by regulating the voltage across the gate and emitter up and down. And the second method is to build a current supply with positive and negative current. And the last one is to apply a constant voltage across the gate and emitter and use a resistance to determine the current flow to the gate, so the gate capacitance can be charged and discharged. The most common and practical way of implementing the circuit is the third option. Generally, IGBTs are driven with a 15-volt turn-on voltage and -5 to -15 turn-off voltage. For this reason, you need two voltage supplies, one for the turn-on, the VG+, and one for the turn-off, the VG-. And these voltages should be chosen as a compromise between different aspects like cost and complexity, the switching speed, conduction losses, and to protect the gate oxide not to exceeding the maximum VGE. It is possible that you only need one resistance value for both turn on and turn off. So you only need one resistor for both processes. But It is also not uncommon that you need to optimize each turn-on and turn-off behavior of the IGBT separately. And to support this, our drivers and in Semikron, we offer separate channels with regulated supply voltages, the VG plus and VG minus, where the gate can be connected. With this, you can adjust them independently. If you see the schematic that is shown here, basically the upper MOSFET as the output stage of a driver that is connected to a positive gate supply will be turned on, so a current will flow through the RG on in this case, and the gate capacitance will be charged, and vice versa for the turn off process. As mentioned before, we need two voltages to switch the IGBT. The gate to emitter voltage, or VGE, basically move between these voltage levels, the VGE on and VGE off. In this slide, we are talking about the turn-on process of the IGBT. It means the gate voltage starts with the VG off down here and goes up to the VG on at the end of the curve. Between the T0 and T1, from the first ramp up of the gate voltage until it reaches the threshold voltage, the CGE starts to be charged. In this period, no current flow through the IGBT between the collector and emitter. As soon as the voltage reaches the threshold at T1, the collector current starts to flow. During this period, at least for most topologies, the freewheeling diodes of the corresponding IGBT is still conducting. That's why we see that the collector voltage here in blue doesn't change in this period. The current cramps up until the overshoot that marks the reverse recovery current from the corresponding IGBT. This current peak means that the diode of the corresponding IGBT stops to conduct, and hence the collector voltage starts to decrease beginning from the T2. The gate voltage is held at the plateau voltage, while the Miller capacitance, or the CGC, is being charged. The collector voltage continues to decrease with slower rate. At T4, the Miller capacitance is fully charged, and the CGE is charged again. When it is finished at the T5, the collector voltage reaches the on-state value, the VCE set. As for the turn-off process of the IGBT, it is basically the same process, but it starts with the VGE on the upper side and down to VGE off at the end of the curve. We also have the Miller effect that holds the gate voltage as long as the CGC, or the Miller capacitance, is being discharged. A point that is not present during the turn-on is the peak at the T3. The collector current is decreasing with a high slope from the operating current and down to zero. This change of current multiplied with the stray inductance across the collector current path, we get an induced voltage on top of the defined collector voltage. But a more practical way of determining the driver output power is to use the gate charge given in an IGBT datasheet. If you take a datasheet of Semikron 3 as our example, we get a gate charge of 2,260 nanocoulomb for gate voltage from minus 8 volt to plus 15 volt. In the diagram section of the datasheet, you will also get shots diagram where it shows the increasing voltage with accumulated gate charge. Sometimes the diagram doesn't show you the whole area that you need in regard of the gate voltage of the driver. In this example, a gate driver has a fixed VGE off of minus 15 volt, but the diagram starts at minus 8 volt. In this case, you may extrapolate the diagram down to minus 15 volt, and if one block means 500 nanocoulomb, we have here an added 1.5 blocks, which means about 750 nanocoulomb. In total, then we have the original 2,260 nanocoulomb and the 750 nanocoulomb from the extrapolation. Here we get approximately 3010 nanocoulomb. With this information, we can move on to the next chapter of the gate driver. Using the gate charts that is obtained from the module datasheet, we can use it to determine which output current should our gate driver have. This simple formula helps us find the average current that is needed in regard of the switching frequency and the gate charts of the module. In many cases, we also use the output power of the driver to generally compare different gate drivers. Another aspect that needs to be considered is the output peak current, because every gate driver is limited with its capability to supply maximum current. In worst case, the peak is determined by the gate voltage that it fixed for a gate driver and the series of resistors that is applied. RG is the external gate resistor in the circuit, and the RG-in is the internal resistor of the module. By the way, the RG-in can mean parallel value of parallel chips in a module. And in practice, the stray inductance reduces the peak value below the theoretical peak current that is calculated in this formula. In the previous example, the Semitrans 3 has approximately 3000 nanocoulomb or about 3 microcoulomb. But bigger module or parallel operation of some modules require bigger output capability of the driver. Here at Semikron, we have an extent of product line. For example, our Skyper 42 LJPV that can deliver up to 4.2 output power for up to 20 microcoulomb gate charge. It can also deliver a peak current of 35 amps, allowing a fast charging of the gate capacitance. It is also to be noted that higher gate charge may require boost capacitor for the driver to secure a stable performance. Using the previous example, it means up to 8 modules of Semitrans 10 can be operated parallel using the Skyper 42 LGPV, or 3 modules in the case of Semitrans 10. But of course, you need to check it in the application, in the end application. Let's move on to the gate resistors. In general, a high gate resistance reduces the current flow through the gate and hence slows down the switching process, and with it increases the switching loss. But not only that, the selection of the gate resistors also affect these aspects, such as the reverse bias safe operating area, the short-circuiting safe operating area, and so on. In the end, the gate resistance selections is a trade-off between these factors. In selecting a gate resistor, we must consider the starting value of a certain module. This we can find in the datasheet as test condition of a parameter. An optimal selection of a gate resistor for a specific application can only be achieved through tests such as double pulse testing. The next aspect is the power dissipation in the resistors, as average value and as peak value. And to determine the average power dissipation on the resistor, a measurement is needed, or you can use the previous equation with the worst case peak current. The curve on the right side shows us the current measured at the gate. In this diagram, it shows current flow at the turn on, whereby at the turn off, we will get the pulse into the negative value. Assuming that the pulse is a perfect triangle that occurs in its period, we can have the RMS value of the power dissipation using this equation, with TP, the period, is approximated using the triangle surface formula, where the peak is the height and the gate charge is the surface area of the triangle. The peak current is the peak power dissipation can be simply calculated with square of current multiplied with the gate resistance. With information about the power dissipation and peak current, the type of the resistor needs to be considered. Depending on the application, use of MELF type to secure operation with high dissipation may be needed. Another tip is to apply the gate resistance as parallel circuit of some resistor. An opening of the gate circuit can cause the IGBT to remain on, and this can be very dangerous for the system in general. And this can be avoided with parallel connection, because the first thing is that the current will be distributed among the resistors, so each resistor doesn't need to take on the whole burden. And the second reason is in the case of compromised resistor, it doesn't necessarily mean complete loss of the gate current path. The next aspect that needs to be considered is the reverse recovery effect that is valid for most of applications. Here we have an example of a half bridge. In this case, the Q2 is turned on. The current through the freewheeling diode D1 starts to decrease. It decreases below 0 amps through the diodes until it reaches the maximum reverse recovery current, the IRRM, as you see here. And if we take a look at the IGBT Q2, the current will be reflected into peak at the end of the ramp up of the collector current, as we see here in the right curves. We understand that reducing the switching loss requires lower gate resistor to make the gate charging faster. This approach is limited by the fact that the maximum reverse recovery current and its slope are depending on the RG on, as we can see in this diagram. Lower RG means faster slope, but also higher reverse recovery current, which will also increase the power dissipation in the freewheeling diode. For the summary of the gate resistor selection, the lower value of the gate resistors leads to lower switching losses, both at turn on and turn off. But if we see this, the example on the right side, the change of the gate resistance strongly affect the turn-on loss. Meanwhile, the turn-off loss only slightly decreases with lower gate resistance. As mentioned before, the lower gate resistance means higher reverse recovery current and hence higher loss due to the reverse recovery effect with this curve here. And we need to take a note that each module has different characteristics. Now we are going to talk about the isolation coordinations. It tells us mainly about the isolation between the primary side or low voltage side in blue and the secondary sides in red, but also between the secondary sides. The isolation is secured by the clearance and creepage distances, as well as the material type, in this case the PCB and the transformers. We use CTI value, the comparative tracking index, to measure the electrical breakdown of the material, where with higher CTI value, it requires lower minimum creepage distances between potentials. The main parameters are the isolation test voltage that reverts to the highest voltage that can be applied, and partial discharge extinction voltage that tells us the quality or condition of an installation. At Semikron, we use the minimum CTI of 175 and typical isolation test voltage of 4000 volt. But in this case, for example, this copper 12, we have the minimum CTI of 400 and the isolation test voltage of 5000 volt. To increase the isolation level, we also have such slit to increase the creepage distances. Here, I want to give you some advice in the application. Generally, short distance between controller and driver is favorable. Separate ground for each signal and power lines should be provided, and a twisted wiring of the signal lines is recommended. The stray inductance should be avoided, while minimum isolation should be still maintained. The same for the connection between the driver and the module. Generally, close distances are recommended. The strong current that flows through the emitter with high slope of the current and stray inductance, a voltage is induced across this LE. And to prevent lower gate voltage due to this effect, it is recommended that we use an auxiliary emitter contact as shown here in the picture. Again, Semikron offers solution to this challenge. To operate various power module, we offer adapter boards in case of use of driver core and plug and play in other case. Here, we give you an example of an adapter board on a SCIM module with Skyper 42 LJ on top of it. The second picture shows us the Skyper 12 PF on Semik's press-fit module. With robust and compact design, they are equipped with emitter contact and mounting pads for parallel gate resistor, among other functionalities. Before we go to its protection feature, here I want to show you the typical block diagram that we have. The first block depicts a driver core with its functions inside it. On the right side of it, we have the passive components in form of an adapter board, and if we have everything in it, then we will have a plug and play driver. You can see here that we have power supply management and the UVALO, the under voltage lockout, on both sides. And the primary sides, we have the short pulse suppression and the dead time, the internally generated dead time. On the secondary side, we have the DSCP that detect the short circuit of the power module. Let's talk about the short circuit protection. In a more simpler approach, the short circuit detection compares the reference VCE and the reflected VCE based on the real VCE during the on-state condition. By the way, the VCE is the voltage across the collector and emitter of the IGBT. If the reflected VCE passes above the reference voltage, which means higher VCE than it should, a short circuit is detected. Semikron's drivers offers the so-called dynamic short circuit protection, or DSCP, that can detect a short circuit even before the VCE reaches the on-state value, the VCE set. If you see the first diagram, the VCE, the dotted line, is the real VCE, and it is reflected and compared with the VCE ref in the form of VCE in. Another parameter is the TBL, the blanking time, which marks the start of the comparison. The last diagram on the right side shows a failure caused by a too short blanking time, where a fake short circuit is detected because the comparison starts when the VCE is still higher than the reference voltage. As mentioned before, if a short circuit occurs, we need a so-called soft turn-off of the IGBT. In real application, we have stray inductance across the power current path, here marked with the L sigma. In the case of short circuit, high current flows through the CE path. What we need to avoid is to turn off the IGBT abruptly. This will cause a steep slope of the current, and as stated in this equation, a voltage will be induced. This voltage will be added to the defined VCE, and its total value can be dangerous to the IGBT. With a soft turn-off, basically we turn off the IGBT with a slower pace. This way, the steep slope of the current can be avoided. Our soft off normally has about 10 times of the normal RG off. Here in the example, we have a delta of 440 volt for the hard turn off, and it is reduced with the soft turn off at about 250 volt. At Semikron, we have an additional channel for these soft off gate resistors, so we can adjust them independently. Other features that a gate may offer is, for example, the under voltage lockout, which monitors the supply voltage. And we have also the short pulse suppression, and as our protection against noises that induced by high frequency switching. Invalid pulses below certain period and below certain level will be filtered out, so we still get a clean rectangle signal at the output. Our drivers also offer different modes of dead time, where you can deactivate it or select different values. The last feature that is included in this presentation is the selectable error mode that is useful in multi-level inverter operation or MLI. In case of error, for example, the short circuit or other error signal, the affected channel will be immediately turned off, but the output of the neighboring channel will not. The driver will forward the error signal to the controller, so it has time to activate the specific turn-off sequence for the MLI application. So the Semikron driver products extend from 1 watt output power up to 4.2 watt output power, and from 15 amps to 35 amps peak current, with increase in isolation through high CTI and an extended slit that I've shown you before. The Skyper 42 LJ-PV and Skyper 12 PV are suitable for operation with up to 1,500 volt DC link voltage. Just an overview of what our drivers offer. Every one of them is equipped with short pulse separation, under voltage lockout, and internally generated dead time, and of course the general failure management. On top of it, you may choose which features do you need for your application. Please take a note that the points inside the brackets means that you need external components to make these features work. Lastly, I want to summarize the key points of this presentation. The IGBT is switched by charge and discharge of the gate capacitance, so we need 2 voltages to turn on and to turn off. We can get the total value of the gate charge by extrapolating the curve given in a datasheet. Using this information, we get the average current that the gate driver should be capable to deliver. The peak current is also something to consider. So, and for the gate resistors, generally, the higher RG limits the current flow through the gate, which results in higher switching loss. In selecting the RG on, you need to consider the turn on and the reverse recovery current as shown here. And for the RG off, you only need to mind the turn off loss. The isolation is secured with the clearance and creepage distances, where the isolation voltage tells us about the strength of the isolations, and the partial discharge voltage gives us information about the condition or the quality of the insulation. Lastly, Semikron offers dynamic short circuit protection and soft off to safely turn off the IGBT in case of short circuit. Other features like dead time, under voltage lockout, and short pulse suppressions are all available in each of Semikron's driver product. I think that's all from my side. And if you want to go more in detail, please take a look into our application note, Gate Driver Basics. Thank you for listening. And if you have some questions, just let me know.
Thank you very much for the great presentation, Adya. To the audience, I did just share the PDF version of this webinar, so you can access that now. And later, we will be uploading the recording of this webinar to our website. I think we'll cut out a couple of those stops there in the middle where we were having PowerPoint issues, but thank you for working through that with us. So we did receive some questions during the presentation, and we can go through these. As I'm scrolling, I'll try to group these with certain categories. And I see the first set of questions that I have are about silicon carbide. Let me scroll to that. So I'll say, what is the difference between drivers for silicon IGBTs and silicon carbide MOSFETs? And of course, what points should be considered when designing the driver for silicon carbide MOSFETs?
So the silicon carbide is still developing right now. The trend is still developing, but we know that it requires different voltage level at the gate. So it needs another turn on voltage and turn off voltage. Until now, there is no one standard what voltage level should it be. Currently, we still do some testing in the hope to find the best specification, to find the best operation of this SiC.
Okay, so Semikron, I guess, is waiting to develop a silicon carbide driver. Does that mean we can use, in the meantime, say one of our Skyper driver cores?
Yes, actually, we have an adapter board as an application sample for the Skyper 42 LJPV that shift up the voltage output voltage of the gate driver, so you can use it to a certain SiC power module.
Okay. I'll go on to some other questions about the resistors. So here's a question about, does the gate resistor require very tight tolerance or special resistors, or are standard board mount resistors okay for this for these adapter boards?
What do you mean? I'm sorry, I don't understand the.
So at one point you had mentioned MELF resistors. Are these different from regular resistors, or what makes them different?
Okay. The MELF resistors typically has the high operating temperature and the high peak current rating. That's why we need to avoid to choose too low specification of the resistor to avoid any burn of the gate resistor. That is what I mean.
Okay, makes sense. And you talked about the plug-and-play drivers, that they go directly onto, say, a SIMX 3 press fit or a Semitrans 10. And those are different from using an adapter board and a driver core. Are the resistors on these still configurable?
So normally we provide fixed resistors for each power module because we have already tested, and this is the optimal values that you need. But if you need an special configuration of the gate resistors, just contact our sales and we can do it. We also provide some customer specific products of these product lines.
Okay, so good to know. Now looking more at the driver cores, I have a couple questions here. For one, it's pretty straightforward. Is the white cover important? There was talk about it being there or not being there. Is that an important feature on the Skyper driver core?
Actually, it doesn't have any function in terms of isolation and so on, but it gives you a protection from a bump. Also, it is just a mechanical protection against a bump directly to the transformers. But for most application, I think our customers know how to handle it with external case or something.
Okay, so mechanical protection for those transformers there. Okay, and you had shown a slide where it has a Skyper 32 Pro, but also a second edition. What is the difference between these two?
So this is actually designed as a one-to-one replacement of the previous type, but we also take this opportunity to make an upgrade in terms of the output power and the reliability.
Okay, so output power, reliability, very good. Okay, here's a long one that I'm reading through, so bear with me. You talked about extrapolation. So say if the data sheet showed -8 volts, and you can take the value all the way down to -15. What about interpolation? Does it work the other direction as well?
Yes. There's the case in power module that they give the gate curve starting from the -15 volt. But for example, our Skyper 42 LJPV starts with -8 volt. Yes, in this case, you can do some interpolation of the gate curve and just take out the some blocks in that diagram that I've shown you, and you will get the total value of that unit with this gate voltages from -8, for example.
Okay. Here's one about the Skyper driver. Do you use ASICs on the Skyper drivers?
Yes. We use it at our drivers, the Skyper 42 LJ and the 42 LJPV, and also the Skyper 12, the R and the Skyper 12 PV. There's some benefits. There is actually what we can see here. This is the ASICs, and with this ASIC, we can spare some components because it includes many functions that a gate driver should have, and we compact it inside one component.
Okay, very good. So I see that there's still more questions coming in. Unfortunately, we don't have a lot of time today. So with that, I'll say, Adya, thank you very much again for the presentation.
Thank you very much.
Certainly. And to the audience, thank you for joining the webinar today. I hope you enjoyed it and you could take away some useful information. Please join us for future webinars and have a great day. Bye-bye.